Evenings are your chance to forget the mistakes you made during the day. So, for the sweetest of dream, you can fare the way. Good evening to one and all present here. On behalf of PG and Research Department of Mathematics, DG VAISHNAV College, I welcome all the PG students and CSIR aspirants. Prayer is the raising of one's mind and art to God, or the requesting of good things from God. Now, Tamutai Vatu followed by college prayer.
நீராறும் கடலொடுத்த நிலமடந்து எழிலொழுகும் சீராரும் வதனமென திகழ்வரத கண்டமிழே எக்கணமும் அதிசிறந்த திராவிடனல் திருநாடும் தக்க சிறு பிறை முதலும் கரித்தனரும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே உன் சீரிழமை திறம் மிகுந்து செயல் மறந்து வாழ்த்துதுமே வாழ்த்துதுமே வாழ்த்துதுமே.
सत्यव्रतं सत्यपरं त्रिसत्यं सत्यस्य योनिं निहितं च सत्ये सत्यस्य सत्यं ऋतसत्यनेत्रं सत्यात्मकं त्वां शरणं प्रपन्नाः वाणी गुणानुकथने श्रवणो कथायां हस्तौ च कर्मसु मनस्तव पादयोर्नः स्मृत्यां शिरस्तव निवास जगत्प्रणामे दृष्टिस्ततां दर्शनेस्तु भवत्तनूनाम् नमो भगवते तस्मै कृष्णायाद्भुतकर्मणे रूपनाम विभेदेन जगत्क्रीडति यो यतः ओम शांति शांति शांति.
This is Safer Workshop, Chase, Crack, Conquer, CSIR Net, which will make the CSIR aspirants to go to the next level. Today, our resource person, Dr. S.P. Vijayalakshmi, Assistant Professor, PG and Research Department of Mathematics, DG VAISHNAV College, Chennai. Now, I hand over the session to you, ma'am.
Thank you, sir. Shall I start now?
Yes, ma'am. Yes, ma'am.
Okay. Good evening to one and all. So in this session, we are going to see about complex analysis. So in the last class, we have seen the singularities, residue theorem. So these are the important topics: singularities, residue theorem, analytic function, power series, complex integration, Schwarz lemma, bilinear transformation, Cauchy's theorem, and the problems based on maximum and minimum modulus principle, open mapping theorem. So these are all the important topics. So in the last session, we have discussed about singularities and the residue theorem and the problems based on singularities and residue theorem. So today, we will discuss about the analytic function. Analytic function related to that is Cauchy-Riemann equation, harmonic function, and then harmonic conjugate, circle, and radius of convergence of a power series. So, and the problems based on this. So, the first one, analytic function. So, the analytic function means the single valued function So defined in a domain which is differentiable at all points of D. So then it is called as analytic function. So what do you mean by differentiability? So differentiability means we say that omega equal to f of z be a single valued function. Then we say that f of z is differentiable if limit z tends to z naught, f of z minus f of z naught divided by z minus z naught exist uniquely. Okay, it should exist uniquely and independent of the path along which z tends to z naught. So it should be independent along the path z tends to z naught. Then we say that f of z is differentiable. So if the function is differentiable at all points of D, then you can say that the function is analytic, right? So if the function, that is, if the function is not analytic at the point, then you can say that that point is a singular point. So in the last class, we have discussed about the singularities, that is isolated singularities, essential singularities, and the poles, and the problems based on this. So the next one is Cauchy-Riemann equation. So actually this is a necessary condition for the function f of z to be analytic. So the Cauchy-Riemann equation is dou u by dou x equal to dou u by dou y. That is ux equal to vy and uy equal to minus vx. So if this condition is satisfied, then we say that it satisfies the Cauchy-Riemann equation. So this is a necessary condition for the function f of z to be analytic. And the sufficiency condition is the partial derivatives, that is a 4 partial derivative, dou u by dou x, dou u by dou y, and then dou v by dou x, dou v by dou y. So all the 4 partial derivatives should exist and it should be continuous, and then it should satisfy the Cauchy-Riemann equation. So that is a sufficiency condition for the function to be analytic. So the necessary condition is only if it satisfies the Cauchy-Riemann equation, then we say that the function is analytic. So the next one is harmonic function. So we say that the function is harmonic if it satisfies the Laplace equation. So the Laplace equation is dou squared u by dou x squared plus dou squared u by dou y squared equal to 0, or dou squared v by dou x squared plus dou squared v by dou y squared equal to 0. So if it satisfies the Laplace equation, then you can say that the function is harmonic. So the next one is harmonic conjugate. So harmonic conjugate is, suppose if u of x comma y be a harmonic function, then we say that v of x comma y is a harmonic conjugate of u of x comma y if the first one is v of x comma y should be harmonic. Okay, v of x comma y should be harmonic and u and v should satisfy the Cauchy-Riemann equation, that is ux equal to vy and uy equal to minus vx, right? So then we can say that v of x comma y is a harmonic conjugate of u of x comma y. So what are the two conditions? The first one is v of x comma y is harmonic, and then u and v should satisfy the Cauchy-Riemann equation. Okay, then we say that v of x comma y is a harmonic conjugate of a function. So the next one is the circle and the radius of convergence of a power series. The circle and radius of convergence of a power series, the circle consisting of all values of z for which the power series summation an z power n converges is called the circle of convergence. Okay, for that is, if you consider the circle mod z equal to r, all the points, that all the values of z for which this power series should be converges in the region. So then that is nothing but the circle of convergence. So the radius r is nothing but the radius of convergence of the power series. So by Cauchy theorem, for the power series summation an z power n, the radius of convergence is given by like this. That is 1 by r equal to limit n tends to infinity mod an to the power 1 by n. And the second one is either 1 by r equal to limit n tends to infinity mod an plus 1 divided by an. So using this, you can apply this in the problem and you can find the radius of convergence. So we'll see a problem under the radius of convergence. So here we need to find the radius of convergence of this power series. So here the series is f of z equal to summation 1 plus 1 by n the whole power n squared into z power n. So here let us consider, see this is a formula, right? So let us consider an to be this one, that is 1 plus 1 by n the whole power n squared. So if you take the nth root, an to the power 1 by n, you will be getting 1 plus 1 by n the whole power n. Right? So 1 by r is nothing but limit n tends to infinity mod an to the power 1 by n. So here an to the power 1 by n is nothing but 1 plus 1 by n the whole power n. So limit n tends to infinity 1 plus 1 by n the whole power n. So we know that this value is e. So 1 by r equal to e means r is 1 by e. So the radius of the convergence of the power series is 1 by e here. So the next one, here we are going to find the limit z tends to 0, z bar by z. So z is nothing but x plus iy. So z bar is x minus iy by x plus iy. So taking the conjugate and then you can simplify. So now you can consider the real part and the imaginary part. So the real part is x squared minus y squared divided by x squared plus y squared. And the imaginary part is minus 2xy divided by x squared plus y squared. Okay, so we need to check whether that is the limit exists or not. Okay, so let us consider along the line y equal to mx. So already we know that it should be unique. The limit exists and it should be unique. Only then you can say that it is differentiable. So if you consider the line along the line y equal to mx, so just substitute y equal to mx. So we'll be getting x squared minus m squared x squared divided by x squared plus m squared x squared. So if you simplify, you are getting 1 minus m squared plus divided by 1 plus m squared. Okay, so this value depends on m. So this is not unique, right? So since this is not unique, you can say that z bar by z, the limit z tends to 0, z bar by z does not exist. So let us consider the next problem. So here, given the power series, that is 2n factorial divided by n factorial the whole squared into 2 minus 3i the whole power n. So we should check which of the following are true. Okay, if it is the part B question, then only one option will be true. For the part C question, more than one option will be right. Okay, so what are the options given? The radius of convergence of the power series is 1 by 4 and the power series converges in the open disk mod 3 minus 3i less than 1 by 4. The power series converges in the open disk of center 3i and the power series is divergent. So we should check which options are true. So first we will find the radius of convergence. So the radius of convergence of the power series is, we know, 1 by r is nothing but limit n tends to infinity modulus of an plus 1 divided by an. So just substitute the value. So what is an plus 1? So this is your an. So replace n by n plus 1. So we'll be getting 2 times n plus 1. So which is nothing but 2n plus 2 factorial divided by n plus 1 factorial the whole square. So into 2 minus 3i the whole power n plus 1. So we are considering only that an plus 1 by an. So we'll be getting 2n plus 2 factorial divided by n plus 1 factorial the whole square divided by an. So an is nothing but 2n factorial divided by n factorial the whole square. Okay, just simplify this. So if you simplify, you're getting 2n plus 2 into 2n plus 1, right? So divided by n plus 1 the whole square. Because this n plus 1 factorial can be written as n factorial into n, right? Sorry, n factorial into n plus 1. So if you cancel, you will be getting 2n plus 2 into 2n plus 1 divided by n plus 1 the whole square. So as n tends to infinity, we are getting the value to be 4. So 1 by r equal to 4. So r equal to 1 by 4. Okay, so the first option, that is the radius of convergence of the power series is 1 by 4. So that is true. A is true. So now the series converges in the open disk modulus of z minus 3i less than 1 by 4. Because the radius is 1 by 4. We are getting the radius of convergence to be 1 by 4. Therefore, you can say that the power series converges in the open disk modulus of 3 minus 3i less than 1 by 4. Okay, and the third option, that is the power series converges in the open disk of center 3i. So the center is 3i. So z minus 3i. So here the center is 3i. So mod z minus 3i is less than 1 by 4. So here it should be z, not 3. Mod z minus 3i less than 1 by 4. So you can say that A option, B and C, all the three are right. So the power series is divergent. So the fourth option is wrong. Okay, just for this power series, we are finding the radius of convergence. So the radius of convergence we are getting r equal to 1 by 4. Hence, you can say that the series converges in the open disk mod z minus 3i less than 1 by 4. So option A, B and C are right. So we'll go to the next one. So here f of z equal to sin x cos hy plus I cos x sin hy. So we should check whether f of z is continuous everywhere, f of z is discontinuous, f of z is analytic everywhere, or f of z is not analytic everywhere. So we should check which of the options are true. So here u of x comma y, that is, this is the real part and this is the imaginary part. So you can consider the real part to be sin x cos hy and the imaginary part is cos x sin hy. So here u and v both are rational function and hence you can say that u and v are continuous everywhere. So here what is dou u by dou x? So just differentiate this with respect to x. We are getting cos x cos hy. And similarly, if you differentiate with respect to y, you are getting sin x sin hy. And dou v by dou x is minus sin x sin hy, and dou v by dou y is cos x cos hy. So from this you can say that dou u by dou x is equal to dou v by dou y. And similarly, dou v by dou x is equal to minus dou u by dou y. So it satisfies the Cauchy-Riemann equation and hence you can say that it is analytic everywhere. So what are the options? F of z is continuous everywhere and f of z is analytic everywhere. Okay, f of z is continuous everywhere since they are rational function and we have verified the Cauchy-Riemann equation and hence you can say that f of z is analytic everywhere. So option A and option C are true. So consider the next one. So here the value of, we need to find the value of m so that the equation 2x minus x squared plus my may be harmonic. 2x minus x squared plus my squared. So this is my squared may be harmonic. So harmonic means it should satisfy the Laplace equation. So the Laplace equation is dou squared u by dou x squared plus dou squared u by dou y squared equal to 0. So that is a harmonic function. So here u equal to 2x minus x squared plus my squared. So just you can find dou u by dou x and dou squared u by dou x squared. So dou u by dou x is 2 minus 2x and dou squared u by dou x squared is minus 2. Similarly, dou u by dou y is 2my and dou squared u by dou y squared is 2m. So here since u is harmonic, dou squared u by dou x squared plus dou squared u by dou y squared equal to 0. So from this you can say minus 2 plus 2m equal to 0 or you can say m equal to 1. So C is 1. So this is a part B question. So only one option will be right. Okay, now the next one, the function f of z equal to mod z squared is continuous and differentiable everywhere, continuous at z equal to 0, but not differentiable at z equal to 0. Continuous everywhere, but nowhere differentiable except at z equal to 0, not analytic except at z equal to 0. So we need to find which of the options are true. So this is actually a part C question. So we need to check whether it is continuous and differentiable, continuous but not differentiable, continuous everywhere but nowhere differentiable, not analytic. So we need to check which of the options are true in this case. So if you consider mod z equal, f of z equal to mod z squared, so f of 0 will be 0. So limit z tends to 0, f of z equal to f of 0. So this is from this you can say that f of z is continuous, because what is the definition for continuous? Limit z tends to a, f of z equal to f of a. So limit z tends to 0, f of z equal to f of 0. So therefore you can say that f of z is continuous at z equal to 0. So the first option. So the next one, f of z equal to u plus iy. So u plus iv is nothing but, suppose if you consider z equal to x plus iy, then u equal to x squared, v equal to y squared. So if you find dou u by dou x, dou u by dou y, dou v by dou x and dou v by dou y, you'll be getting dou u by dou x is 2x, dou u by dou y is 0, dou v by dou x is 0 and dou v by dou y equal to 2y. So only at the origin, you can say that the CR equations are true. So only at the origin, dou u by dou x will be equal to dou v by dou y. And similarly, dou u by dou y will be equal to minus dou v by dou x. So only at the origin, it satisfies the CR equations. So therefore, you can say that the options are C and B. The next one, the function f of z equal to imaginary part of z divided by mod z, where z is not equal to 0 and 0 when z is equal to 0. So we need to check whether it is continuous at z equal to 0, differentiable at z equal to 0, not analytic at z equal to 0, discontinuous at z equal to 0. So here f of z is given to be imaginary part of z divided by mod z. So u equal to, let us consider u equal to y divided by root of x squared plus y squared and v equal to 0. So we need to check whether it is differentiable or continuous at 0, not analytic or discontinuous. So let us consider along the line y equal to mx. So if you consider along the line, so just substitute y equal to mx. So we'll be getting mx divided by root of x squared plus m squared x squared. So as x tends to 0, you're getting m divided by root of 1 plus m squared. So the value depends on m. So it is not unique. Therefore, you can say that u is discontinuous at z equal to 0. And hence you can say that f of z is discontinuous at z equal to 0. So f of z is discontinuous at z equal to 0. So that is the answer for this problem. So the next one, let u be the harmonic function. Then again we have to check which of the following are true. So again this is a part C question. So more than one answer will be true. So the first one, harmonic function satisfies the formal differential equation dou squared u by dou z bar equal to 0 and u be a harmonic function, then u will satisfy a Laplace equation. So the next one, dou u by dou z bar equal to 1 by 2 dou u by dou x minus 1 by 2i dou u by dou y. The last one, a harmonic function do not satisfies the formal differential equation dou squared u by dou z bar not equal to 0. So we need to check which of the options are right. I repeat. So the first one is harmonic function satisfying the formal differential equation dou squared u by dou z bar equal to 0. The next one, u be the harmonic function, then you will satisfy the Laplace equation. So the third one, dou u by dou z bar, which is equal to 1 by 2 dou u by dou x minus 1 by 2i dou u by dou y. The last one, a harmonic function do not satisfies the formal differential equation dou squared u by dou z bar not equal to 0. So we need to check which are the options are true. So first one, z equal to x plus iy. So if z equal to x plus iy, then we know that the real part, that is x is equal to half of z plus z bar and y equal to 1 by 2i z minus z bar. So the real part is nothing but x and the imaginary part is y. So the real part is 1 by 2 times z plus z bar, and the imaginary part is 1 by 2i z minus z bar. So since u is a harmonic function, definitely it satisfies the Laplace equation, that is dou squared u by dou x squared plus dou squared u by dou y squared equal to 0. So now we will find dou u by dou z bar. So dou u by dou z bar is nothing but dou u by dou x into dou x by dou z bar plus dou u by dou y into dou y by dou z bar. So if you differentiate, you will be getting 1 by 2 times dou u by dou x, because dou x by dou z bar. So if you differentiate this with respect to z bar, you will be getting 1 by 2. So 1 by 2 into dou u by dou x, and similarly dou u by dou y by dou z bar. So dou y by dou z bar is nothing but here you are having minus, so minus 1 by 2i. So you will be getting minus 1 by 2i into dou u by dou y. So dou squared u by dou z bar is nothing but, you can rewrite this as dou by dou z of dou u by dou z bar. So dou u by dou z bar is nothing but this. So again you have to differentiate this with respect to partially with respect to z. So if you differentiate, you will be getting 1 by 2 dou squared u by dou x squared into dou x by dou z plus 1 by 2 dou squared u by dou y dou x into dou y by dou z minus 1 by 2i dou squared u by dou x dou y into dou x by dou z plus 1 by 2i dou squared u by dou y squared into dou y by dou z. So if you simplify, you can say this is nothing but 1 by 4 times dou squared u by dou x squared, because dou x by dou z 1 by 2. So you'll be getting 1 by 4 into dou squared u by dou x squared plus 1 by 4i dou squared u by dou y dou x. So you're combining this two, and then minus 1 by 4i into dou squared u by dou x dou y. Again dou x by dou z is 1 by 2, so you'll be getting minus 1 by 4i dou squared u by dou x dou y, and then plus 1 by 4 dou squared x by dou y squared. So these two terms will get cancelled, and you will be getting 1 by 4 into dou squared u by dou x squared plus dou squared u by dou y squared. Since u is a harmonic function, we know that dou squared u by dou x squared plus dou squared u by dou y squared equal to 0. So therefore, here you will be getting 1 by 4 into 0, so which is equal to 0. So what are the options are right? So a harmonic function satisfies the formal differential equation. So we got dou squared u by dou z bar equal to 0. So this option is true. And the second one, u be a harmonic function, then u will satisfy the Laplace equation. So this is also true. And the third one, dou u by dou z bar equal to 1 by 2 dou u by dou x minus 1 by 2i dou u by dou y. So we also got that. So dou u by dou z bar equal to 1 by 2 dou u by dou x minus 1 by 2i dou u by dou y. So you can say option A, B and C are true. Okay, since we got dou squared u by dou z bar equal to 0, so definitely the fourth option will be wrong. So the answers are A, B and C. So all A, B and C are true. So this is a part C question. So the next one, if you consider f to be a function from C to C. So this is a complex valued function, that is from a complex plane to a complex plane, given by f of z equal to mu of x comma y plus iv of x comma y, and given v of x comma y equal to 3xy squared. Then we have to check which of the following are true. That is, f cannot be holomorphic on C for any choice of u. And the next one is f is holomorphic on C for a suitable choice of u. The third one, f is holomorphic on C for all choices of u. And the last one, v is not differentiable as a function of x and y. So the first one is f cannot be holomorphic on C for any choice of u. Second one, f is holomorphic on C for a suitable choice of U. Third one, F is holomorphic on C for all choices of U. And the last one, V is not differentiable as a function of X and Y. So we will check which of the options are true. So first one, if for F to be holomorphic, V has to be the harmonic function. So if F to be holomorphic, then V should be the harmonic function. So here, given that V of x comma y equal to 3xy squared. So we will find Vx. So Vx is 3y squared and Vy is nothing but 6xy. Vxx. So Vxx is 0 and Vyy. So Vyy is 6x. So Vxx plus Vyy. So if you find the Laplace equation which is not equal to 0. So therefore you can say that F is not holomorphic on C for any U. F is not holomorphic on C for any U. Okay, so the option A is true, right? Since option A is true, option B will be false. F is holomorphic on C for a suitable choice of U. So this is not true. And similarly, F is holomorphic on C for all choices of U. So that is also not true because we have verified the first one, that is F cannot be holomorphic on C for any choice of U. So for F to be holomorphic, then V has to be harmonic. So we have checked whether V is harmonic, but V is not harmonic. Therefore, you can say that F cannot be holomorphic. F cannot be holomorphic on C. So the first option is true. So since the first option is true, you can say that the second option. So the second option is F is holomorphic on C for a suitable choice of U. So the B option is false. And similarly, the third one, F is holomorphic on C for all choices of U. So that is also false. So V is not differentiable as a function of X and Y. So that is true. So here A and D are true. The A option and the D options are true. So we have discussed some problems under the analytic function and then the Cauchy-Riemann equation and under harmonic functions and then the radius of convergence. So the next topic is we will be discussing about the Cauchy theorem, Cauchy integral formula and the Morira's theorem. So all these things we will discuss in the next class. So in the next class, we will discuss about the Cauchy integral formula and the Morira's theorem, Liouville's theorem and the maximum modulus principle. So in the problem based on that. So we will have the quick introduction about the Cauchy integral formula and the simply connected domain. So we say that function that is a simply connected region. We say that the function is connected region or the domain is said to be simply connected if the closed curve C is contained in D as its interior contained in D. That is, it should not have any hole. If the domain does not has any hole, then you can say that the domain is a simply connected domain. The multiply connected domain means that is a multiply connected region is bounded by more than one curve. Suppose if you consider the concentric circles. So that is nothing but the multiply connected region. That is a multiply connected region will have a hole. Okay, and then the Cauchy integral formula. So the Cauchy integral formula, suppose if you consider f of z to be the analytic function in a simply connected domain enclosed by the rectifiable Jordan curve, then f of z naught equal to 1 by 2 pi I integral over C f of z divided by z minus z naught into dz. So z naught is any point. So this is a Cauchy integral formula. So we'll be having a number of problems based on the Cauchy integral formula. And similarly, the Morira's theorem. So Morira's theorem is nothing but the converse of the Cauchy's theorem. That is, if f of z is continuous in the simply connected domain, then you can say that integral over gamma f of z dz equal to 0. So that is a Morira's theorem, which is nothing but the converse of the Cauchy theorem. So again the Liouville's theorem. So Liouville's theorem is if f of z is analytic and satisfying the inequality mod f of z is less than or equal to m for all values where m is a positive constant, then you can say that f of z is a constant. So we have a number of problems based on this theorems. So we need to understand a concept and then we have to apply that in the problems. So in the next class, we will discuss about the problems based on this concepts. So I want everyone to work out the problems under this analytic function and then the harmonic function and radius of convergence, etc. So we have discussed around 9 problems today. So I want you to try some more problems. Okay, thank you.
Thank you, ma'am.
Thank you, sir.
On behalf of PG and Research Department of Mathematics, DG VAISHNAV College, thank you, ma'am, for spending your valuable time in our C4 session. Really, it's a wonderful session to all our students, research scholars, and teachers. I would like to thank Professor R. Venkatramanan, Head, PG and Research Department of Mathematics, for organizing this C4 workshop. Our next C4 session will be held on tomorrow at 11 a.m.